All right, so now we're on to part 2, which is, again, non-calculator. We're going to be graphing the polynomial functions without a calculator. Graphs of polynomials. So when we talk about graphs of polynomials, are smooth and continuous. There's no breaks, no gaps, no holes, or sharp turns. So I can follow without lifting, okay? The domain is from negative infinity to positive infinity. And we know this because it goes forever to the left and forever to the right, okay? The end behavior of the polynomial depends on the degree of the function and the sign of the leading coefficient. And these are things that we've already learned thus far. So we've talked about our dance moves, right? If you had a positive even, so your leading coefficient is positive and you're an even degree, remember that was us raising the roof, okay? If you had a negative even function, so your leading coefficient was negative and your degree is even, that was us shimming on down, right? Because on the left and right hand side. And then if you had a positive odd function, that was us staying alive. We're going forever to infinity on the right and going to negative infinity on the left. And if you had your negative odd, that's us going forever to negative infinity on the right and positive infinity on the left, okay? So these are things that we know about our polynomial functions thus far. Now, multiplicity. As you notice that in part 1, we had factors that had powers on them, right? So what that is called multiplicity. So the multiplicity, the number of times a given factor appears in the factored form of the equation of a polynomial. That is its multiplicity, okay? When there is not a number, that's called a single root. For single roots, when we are graphing them, it is just going to cross the x-axis. So it crosses x-axis, okay? So our single root example would be if we just had x minus a. There's no power here. It's Casper the Friendly One. So this is a single root at a. So when you graph it, it's just going to cross at a at this point. Okay? A double root is going to be, the math term is tangent to the line. It's tangent, but in our terms, we call it, it's going to touch. It's just going to sit and touch. I call it a kiss, a little peg. It's going to just peg the line, okay? I know that's crazy, but it's tangent to the x-axis. And you'll see why I call it a peg to the x-axis. So if I have x minus a, and this has a 2 or any even number. So double roots are going to be any even. So this is our even root. X minus a to the 2, x minus a to the 4, x minus any even root is going to happen. What ends up happening is when you look at the graph, at that point where a happens, we are, notice that remember I said I call it, it kisses the line, it gives a little peck and bounces back up, okay? It no longer is going to continue or cross. It's tangent, okay? A triple root, which are going to be our odd powers other than 1. So for a triple root, it also crosses, but it crosses at a slower rate. So it crosses the x-axis. It's just at a slower rate. So the rate of crossing is a little slower, meaning that it's not going to go as fast through the rate, as fast through the x-axis. So I like to call these, I know it's going to sound crazy, drive-bys. So here is my a, and if it's cubed, it's going to curve and speed off. So like it's still increasing, it just slows down a little bit and then speeds off, okay? So the rate is going to change, all right? The degree of the polynomial is also the number of complex roots, which means in total, whatever the degree is, that's the maximum number of what we're going to eventually learn, real and imaginary roots you can have in total. That's a later for pre-cal problem. But for us, it's a total of possible roots. So we're only working with non-complex. So therefore, for right now, it's the total number of roots you can have. So let's get into this diving. Let's dive into graphing. How to graph. So the first thing you're going to do is you're going to make sure your polynomial is factored. So you're going to factor the polynomial completely. The next thing you're going to do is find the x-intercepts and set each, in order to find the x-intercept, you're going to set each factor equal to 0. Next, you're going to find the y-intercept, which means you're going to evaluate f of 0. And then you're going to use your end behavior to determine how to start the graph. So remembering, how do we determine our end behavior? Well, our end behavior depends on our degree and our leading coefficients. All right, so let's dive in. So up first here, we have f of x equals x times x minus 1 times x plus 4, okay? It's already factored for us, so step 1 is done. So 1, done, factored for us. Step 2 is we're going to take each factor and set it equal to 0. So we have x equals 0, which means that we have an x-intercept at 0, 0. We have x minus 1 equals 0, which means that we have x equals 1, and we have an x-intercept at 1, 0. We have x plus 4 equals 0, which means that we have x equals negative 4. That looks terrible. Let me fix it. Equals negative 4. And so our other x-intercept is going to be at negative 4, 0. Okay, so that's step 2. All right, so I'm going to go ahead and plot them for myself really quick. Here's 0, 0. And then we're going to go to 1, 0. I'm going to put 1, 0 right here. That's going to be my 1, 0. And then I'm going to go over here and put negative 4. So negative 4 and 1. Next step is our third step is to find our y-intercept. To find our y-intercept, we're looking for f of 0. F of 0 means everywhere there's a 0, I'm going to plug in. Well, in this case, it's really easy because what happens? This guy makes everything 0. So f of 0 is 0, which is why I have this. Okay, so my y-intercept is one of my x-intercepts. All right. And then our fourth step is to determine our end behavior. To determine our end behavior, we are looking at we talked about in the last part, we are looking at our leading terms and multiplying them. Okay, so our leading terms for each one of our factors and multiplying them. You do not have to multiply fully if you don't want to. You just need to make sure you can identify, is it a positive or negative leading coefficient, and is it an odd or even degree? Okay, so we have positive x times positive x times positive x, which is going to equal positive x to the third. So therefore, we have a positive odd polynomial. All right, so we have a positive odd polynomial. That means that on the right side, I'm sorry, I went the wrong way. On the right side, we're going to start off positive, and on the left side, we're going to end negatively. Okay, so when we draw this from left to right, we're going to focus on the fact that I have to get from here to here while also going through my x-intercepts. All right, so let's do our best sketch. Notice at this time, we're not really paying attention to the y's. We're only paying attention to everything else. So I'm going to go through this guy. I'm going to go through this guy. And oh, that was terrible. Let's try that again. I'm trying to make my smooth and continuous line. My curve, not line. I'm still terrible. Let's try that again. Go through that boy. There we go. Close enough. Close enough. Better than what I did the first time. And that would be my sketch. Okay? So this is a rough sketch of what this would look like. All right? Without knowing any other values or finding other values, this is just an outline of what this could potentially look like. All right? I just know that I have to go up. I'm increasing. Then I'm decreasing. And then I'm increasing. And I'm a third degree polynomial. All right? Let's try it again. So on example 2 for you, example 6 for me, this is not fully factored. So before we do anything, we have to factor. In order to factor this, we're going to always start off with GCF. So you ask yourself, is there a GCF? And myself is going to say, yeah. You can divide everything by x. So when I factor out x, I'm left with x squared minus 4x plus 4. Okay? This is a simple trinomial factoring because my leading coefficient is 1, so I'm hoping that I can find what multiplies to give me 4, but adds to give me -4. And that would be a -2 and a -2. So this gives me x times x minus 2 times x minus 2. That would be my factored form. Okay, so from my factored form, I can condense it to x times x minus 2 squared. Boom. All right, then the next step is to find my x-intercepts and to describe what's happening with them. So I have x, so x equals 0, so I'm going to be at 0, 0. And then I have x minus 2 squared equal to 0, which means that x equals 2, and I'm going to be at 2, 0. However, 2, 0 is special. It is special because of this 2. That means that I have a double multiplicity there. And that double multiplicity means that when I graph this, I'm going to be kissing the line, right? I'm going to be at 2. So I don't cross, I am bouncing and going right back up. And that's because of this 2, that double multiplicity, all right? So paying attention to this means that when I graph, I have to make sure at 2 that I'm either going to go pew pew somehow and come back, all right? 3 is your y-intercept, your f of 0, and because we have an x-intercept at 0, that means that our y-intercept is 0. And then lastly is figure out the degree of our polynomial, and the degree of our polynomial is super duper easy if we go back to the original. So going back to the original, it was here. Our degree and leading coefficient. So our leading coefficient is positive, and our degree is a third degree, which makes it odd, right? So third degree odd, which means that again, on the right side, we're going to be going up, but on the left side, we're going to be going down. So now we're going to put all of this on the graph. So I'm going to graph my x-intercepts. So we're at 0, 0, and we're at x equals 2. I'm going to put it right here. So this is 2, that is 0. And I have to come from the left and make it so that I can go up. So coming from the left, we're doing this. At 2, we bounce. And that's how we continue on to positive infinity. And that is what your graph would look like, following all those key features. All right, our next example. So we have another example again. First thing you should always do is check to see if there's a GCF, and myself is like, oh yeah, there's a GCF. Your GCF here is negative x to the third, okay? My leading coefficient is negative, so that makes my GCF negative, and my smallest variable on my power is x to the third, so I can factor that out. So factoring out negative x to the third. Okay, so when we factor out the negative x cubed, we're left with positive x plus 3. And that's what we're left with, because a negative divided by a negative is positive. And so now we're fully factored. So now that we're fully factored, we can go ahead and find our zeros. So the first thing we have is we have negative x cubed equal to 0, which means that we are at x equals 0. And at 0, 0, we have a multiplicity. That multiplicity is 3. And so because of that, we have an odd multiplicity. Because of that odd multiplicity, we know that, quote unquote, at 0, 0, we're going to be doing a little bit of a drive-by, like a little slow down and go. All right. The next one is x plus 3. So we have x plus 3 equals 0, which is x equals negative 3. And so our x-intercept is going to be negative 3, 0, and it's just a single root. So that's all it is. All right. On to number 3. On number 3 is our y-intercept, and because we have 0, 0, that means our y-intercept is also at 0. Last is identifying our leading coefficient and our degree. So going back to the original, because it was already in standard form, we know that our leading coefficient is negative. So we have a negative leading coefficient, and our degree is 4, so we have an even degree. So the negative lets us know that on the right side, we're going to be going towards negative infinity, and because it's even, that means on the left side, we're going to be doing the same thing. And now we're going to put it all together. So we have 0, 0. So we have 0, 0. Then we have negative 3. Negative 3. And we're going to follow. So starting from the left, we're going to cross negative 3. We're going to come up. At 0, 0, we have a slowdown. Okay. And bam. There is our graph. Okay, so then we have our last example here. And again, it's not factored, so we're going to factor because the first step is to factor. So looking here, I have a GCF of x squared. So when we factor out x squared, we get x squared. And we're left with x squared minus x minus 20. So we're asking ourselves what multiplies to give us 20, but adds to give us negative 1. That would be x squared times x minus 5 times x plus 4. Okay, so those are that it's in factored form. Now that we're in factored form, we can find our zeros. We have x squared equals 0, which means that we have x equals 0. So at 0, 0, we have a double. Okay. And then we have x minus 5. So x minus 5 equals 0. Means that x equals 5. It's a single, so we're going to just cross. And then we have x plus 4 equals 0, which means that x equals negative 4. X equals negative 4, and at negative 4, 0, again, it's just a single. So you had a double, and the reason why we had the double is because of the square, right? All right, moving on. The next thing we are supposed to do is our y-intercept. But our y-intercept is f of 0, and it's going to equal 0. And the reason why it equals 0 is because we already know that it goes through 0, 0. All right, next is our degree. So going back to the original, we're looking at our leading term, our degree, and our leading coefficient. We have a positive leading coefficient, and we have a fourth degree, which is even. So that means that on the right side, we're going up. And if we're going up on the right, and because it's even, we're also going up on the left. So now let's get to graphing. So we're going to graph 0, 0. We're going to graph 5, 0, and put 5, 0. And we're going to graph negative 4. Okay, so coming from the left, we're going to start from positive y's. So we're coming down. And then at 0, we have a double, so we bounce. And then we're going to continue on out to 5. So again, right now, we're not worried about, it's a little more curved. We're not really worried about the y values exactly. We're just making sure we understand the shape of what the graph looks like. And that will be our last example for part 2 of 3C.5.